Welcome to Chapter 5, the final chapter of quantum computing hardware. Chapters 2 through 4 walked through the platforms one at a time, and each ended in the same place. The physics works, and the engineering is unfinished. This chapter is about that engineering, because that is where the next decade of the field will actually be decided. We ask why a qubit count is the most misread number in the field, what error correction really costs, and why the cost is payable at all, how wiring and heat set limits, why modularity is the structural answer, and how to read a benchmark without fooling yourself. Start with the most misread number in quantum computing, the qubit count. If a 2-qubit gate fails with probability epsilon, a circuit of m gates survives with roughly e to the minus m epsilon, so the usable circuit depth is of order 1 over epsilon. Notice what does not appear there, the number of qubits. Picture a device as offering a rectangle, width times depth. Doubling the qubits doubles the width and does nothing for depth. Having the error rate doubles the depth, and it does so for every qubit at once. Worse, bigger chips are harder to fabricate, wire, and calibrate, so naive widening tends to degrade depth. A logical qubit is a machine, not a qubit. The state lives non-locally across a block of physical qubits, so no single one holds it. We repeatedly measure syndrome operators that reveal whether an error occurred and where, without revealing the encoded state. A classical decoder infers the correction in real time, so a fault-tolerant machine contains a substantial classical computer running continuously. The surface code suits planar chips because its checks involve only neighbors, and its threshold sits at roughly the 1% level. Overhead is of order 1,000 physical qubits per logical qubit, an order of magnitude and a moving target. A code is characterized by its distance d, roughly how many individual errors must conspire before the logical information is corrupted. Cost grows polynomially. A surface code patch is a d by d lattice, so the qubit count grows like d squared. The logical error, though, falls exponentially, schematically as the ratio p over p threshold raised to the power d plus 1 over 2. Below threshold, that base is less than 1, so exponential beats polynomial, and that single inequality is the whole reason fault tolerance looks buildable. Above threshold, the base exceeds 1 and adding qubits makes things worse. Getting below threshold is a precondition, not an optimization. Let us make the asymmetry concrete, with a warning first. This is a pedagogical toy formula, not any real code's performance. We fix the prefactor at 1 and the threshold at 1% purely for illustration, and real logical error rates depend on the noise model, the decoder, and the syndrome circuit. At a physical error rate 1/10 of the threshold, the logical error falls from 1 times 10 to the minus 2 at distance 3, to 1 times 10 to the minus 7 at distance 13, while the qubit cost grows only about 19 times. Above threshold, the same table climbs instead of falling. Suppose the physics is solved. You still have to talk to every qubit. Each qubit needs at least one control channel, so lines grow linearly with qubit count while space, cooling power, and money do not. A refrigerator's cross-section and a vacuum chamber's optical axis are fixed. Every line running from room temperature down to the coldest stage carries heat by conduction along the metal and through dissipated signal power. Cooling power at the coldest stage is minuscule, and it is a hard budget. Exceed it and the fridge simply warms up, degrading every qubit at once. Qubit fabrication and qubit access scale differently. 2 directions try to break 1 line per qubit. Frequency multiplexing already helps readout. Qubits with distinct resonator frequencies share a line, though it demands fabrication precision and does not remove individual control. Cryogenic control electronics moves signal generation into the refrigerator, but transistors dissipate power, and power at the coldest stage is exactly the scarce resource, so realistic designs sit at warmer intermediate stages and trade signal quality against heat. Ions and atoms meet the same pressure in optical form. Meanwhile, calibration drifts. Parameters grow with qubits and connections, crosstalk couples them, so beyond a certain size the machine must calibrate itself. If one device cannot grow arbitrarily, build many small ones and connect them. A monolithic processor gives direct, fast interactions, but yield falls as area grows. A modular one uses units small enough to fabricate reliably, at the cost of a connectivity hierarchy that compilers must respect. Photonic interconnects lead. A stationary qubit emits a photon entangled with its state. Photons from two modules interfere at a beam splitter and are detected, and a successful pattern heralds entanglement, so failures are known and simply retried. Superconducting modules additionally need microwave-to-optical transduction. Trapped ions instead shuttle the qubits themselves between trap zones without heeding the motion that gates rely on. When you meet a hardware claim, work through the 5 questions on this checklist. 2 devices with the same qubit count can differ by orders of magnitude because the count says nothing about error rates, connectivity, gate speed relative to coherence, physical versus logical qubits, or whether every qubit works on the day. Randomized benchmarking is the standard gate measure, but it reports an average over random gates, can underreport coherent errors, and says nothing about crosstalk unless designed to. Quantum volume is the best-known holistic attempt, demanding width and depth together, yet any compression into one dimension discards information and can be optimized as a target. The gap to a fault-tolerant machine is not one breakthrough wide. It is an engineering marathon whose defining feature is that every layer must scale together. Qubits must get better, not just more numerous, because the margin below threshold sets the overhead. Control must scale sublinearly in wires and calibrate itself. Cryogenics and vacuum must supply cooling, access, and stability at far larger scale. Interconnects must make modularity a gain rather than a bottleneck. Classical decoding must keep up in real time, and software must turn all of it into something you can program. A weakness in any one layer caps the system, and no platform has all the answers. That completes quantum computing hardware. Chapter 1 asked what a qubit must physically provide. Chapter 2 took apart superconducting circuits. Chapter 3 covered trapped ions and neutral atoms. Chapter 4 surveyed photons, spins, and the topological proposal. And this chapter showed why the remaining work is a scaling problem across every layer at once. The series builds on Introduction to Quantum Computing, which supplies the algorithms, the noise picture, and the vocabulary behind these machines. Specifications will keep moving, but the principles here should let you read the next decade of announcements with informed eyes. For the full written articles, check the AI Terakoya knowledge base.